Okay, folks, what we got going on here is a little review of gas laws. Now, you should have looked at those three videos, that I had put on last week, and I hope you did okay with those. There was a bunch of notes I put on about gas laws, problem solving. Hope you get them. Let's do a quick review. So we have so far Boyle. You don't really need to know the names of them, but I want to put them out there anyways. Boyle's Law. You have Chuck. Chuck's my favorite. That is Charlie's Law. Then we have Gay-Lussac's Law. And 3. The only problem with these is they only have 2 variables in them. And most of the time in chemistry, you got 3 things going on. It's very rare that you'll have, for example, temperature being held constant, pressure being held constant, or volume being held constant. That usually doesn't happen. So, what's a better one than that one? Take all 3, combine them. Now, if you take all 3 and combine them, let's think, what would you call that? I don't know. Combined gas law? Boom, very good, Billy. All right, so take all those, combine them, and you got yourself the combined gas law. P1 V1 over T1 equals P2 V2 over T2, combined gas law. If you have temperature in any of the gas laws, you have to make sure that you have it in Kelvin. Kelvin, not Hobbs. Kelvin, Hobbs. No, you don't want Hobbs, you just want Kelvin. It's fine. Little kid, tiger, you with me? All right. So you want to make sure that these temperatures are in absolute temperatures. You can never go wrong with absolute temperature. You usually will go wrong with Celsius, so make sure you're in Kelvin. Okay, so add 273 whenever you're given a Celsius temperature. And you got yourself in Kelvin. Okay, so those are the basic gas laws. Now at this point, we should also go into the 5th, number 5 gas law, the big kahuna. Some would say the most important of all. Yeah, and maybe me too. All right, here we go. The big kahuna. Well, I'll make a little n. N, RT. Is that bothering some of you? Is it? I mean, some of you, let me erase it for you. Okay. Is that better? Okay, good. Don't want you freaking out on me. Okay. Ideal gas law. Ideal gas law. Ideal gas. Usually a few hours after you eat beans. That's not Corona. So, let's see. Why is this one better? Well, it has this in here. Pressure, volume, temperature, and N. Moles. We all know the most important thing in Chem 1 is to be able to convert moles to grams, grams to moles. Okay, now, this has something to do with the number of particles. So let's say moles. In fact, moles, if you remember how to get it, you take the amount of mass that you have. Maybe you've got 8 grams of silver. And you want to know how many moles that is, you divide it by the molecular weight from the periodic table. Okay, that will give me moles. So, this has the number of particles. Now we can get mass. We can remember going back several weeks ago, we can convert mass to moles, Chicago, San Diego, Boston. Yeah. And you can go from moles to mass to mole, but you can also go to the number of particles. And the number of particles that you have does matter when it comes to gas laws. For example, if you have a container, we'll call it container A. And a second container, we'll call that container B. It's deep. And container A has 5 gas particles in it. Same volume as container B. Container B has 10 gas particles in it. Which one's going to have more pressure? which one's going to have more force applied to the outside of that container because you have more particles. That's okay. You can say, you know the answer. You do. Container B. More particles, more pressure. More pressure. If you don't have a rigid container, you'll have a expanding volume. So the number of particles makes a difference. So this gas law here, ideal gas law, takes into consideration how many particles that you have. Okay, now the reason it's called the ideal gas law, there are certain conditions called ideal gas conditions, which have to be maintained for this gas law to work. And under normal laboratory conditions, those conditions are met and it works. So we'll get into those conditions a little bit later. We'll do another video because videos are so fun on ideal gas law assumptions. Okay, but for now, let's just say Spad Larry's going to work. Okay. All right, so let's take the ideal gas law and make a substitution in. Yeah, let's give it that. We'll substitute in mass divided by molecular weight, which is how we get moles, times RT. Okay. This comes in handy dandy notebook. You can use this version of the equation to solve for molecular weight, or you can use this version of the equation, move it around a little bit and solve for density. Now I put how I did that step by step on Canvas last week, but let me go through it one more time because I want to do one problem using this version. Okay, so let's say I want to solve for density of a gas. Density, think. Density. What's density equal to? Oh, I don't know, I don't remember. Oh, I do. Oh, Billy, what is it? Well, density is mass divided by volume. Very good, Billy. So density is mass over volume. Oh, we have that. We have mass, we have volume. Move things around, set it up for density. So to get mass over volume, M over V, I will have to take RT, move it to this side of the equation, V over here, MW, move everything around. What do you get? You have MW times P, and it doesn't make any difference which order you put those in. So I moved this one over here, switched it. Then we take RT and bring that down. Then we have use the ideal gas law now set up to solve for the density of a gas. Okay, let's try a problem using that. Let's try one problem using this ideal gas law before we get into moving on to the next one. Okay, let's see. All right. Okay, here we go. Whew, I'm so pumped. Let's say that you want to figure out the density of some gas. And you know the molecular weight of the gas. Maybe it's water vapor. Water vapor is a gas. Vapor is a gas. So that'd be H2O gas. And H2O has a mass of 18 grams per mole, molecular weight. So the pressure is, maybe it's a low pressure day. A lot of water vapor in there. Maybe it's a little rainy day. So let's say the pressure is 1 point, no. Let's go less than 1 point because 1 would be average. Let's go 0.95 atmospheres. ATM. 0.95 ATM. And you know atmospheres is ATM. And you know what an ATM is. It's where you get money. ATM. Where you get money. Tough crowd. It's also what Dorothy was saying. ATM, where are you, ATM? She was trying to get money. She had to find ATM. ATM. Dorothy, Wizard of Oz. Again, tough crowd. Right. There are 3 different pressure units. You've got atmospheres, you have millimeters of mercury, and who remembers? Kilopascal. Kilopascal. Poor Pascal. Why do you want to kill him? Kilopascal. Okay. So these different pressure units, it matters what pressure unit you're in. And the reason it does is because this R value, what's R? What's R? It's called the gas law constant. So you need to come up with an R value that'll go into the equation. And you have today's choices. 1, 2, 3. It depends what unit you're using for atmospheres. We're using atmospheres. What unit you use in the problem. Are you using atmospheres, millimeters of mercury, kilopascals? Okay, you should write these down. You should know these. You should just know them. Write these down. Here we go. R for ATMs. R for millimeters of mercury. And R for kilopascals. It's a little k, actually. So kPa. I use a cursive little k because otherwise it looks like a big K and it's all confusing. So, R for atmospheres, what would that be? That's the one we're using. That's 0.0821. Kilopascals is 8.31. Millimeters of mercury, R value, 62.4. There's a bunch of units that go with them, but just trust me, they all cancel out, so who cares? Now, so which one are we going to use? Well, come on, Billy. We know that we are using 0.95 ATM, so I'm going to use the R value of 0.0821 right there. And let's say it's a typical nice spring day. It's about 20 degrees Celsius. 20 degrees Celsius is my temperature. So T is 20 degrees Celsius. Are you ready? Let's do it. Okay, let's see. Make some room. We'll do the math up top. Okay. Density equals a molecular weight. Now this is water vapor. Water vapor, molecular weight of water. H2O, 2 hydrogens, 16 for oxygen, 16 plus 2. Anybody got a calculator? Crank that out. Oh, wait. 18? Okay, 18. So 18, it's grams per mole. I'm not going to play around with the units here. Just trust me, trust me. I'm not wearing a tie. I'm wearing my Disney shirt. You can trust anybody wearing a Disney shirt. Trust me, they'll work. Okay. So this pressure was 0.95. Standard air pressure, average air pressure is 1 when it comes to atmospheres. That's why in chemistry we like using atmospheres, because 1's an easy number. 1. It's also a lonely number. The loneliest number that you ever knew. I should write songs. I got great lyrics. Okay. R. Which R are we going to use? I'm going to use 8.31. It's my favorite number, 8. No, don't do that, Billy. You need to use a proper atmosphere. 0.0821. The atmosphere R value. Got to be in the right one. 20. Temperature's 20. Just put the 20 in there. You'll be all set, right? No, because 20 is in Celsius. You need it in Kelvin. Kelvin. 290. Well, let's see. 273 plus 20. 273. Carry the 6. Minus 8. 293. So 293. Okay. Let's see. Get the calculator out. Handy dandy notebook. And crank this out. Okay, here we go. 18 times 0.95 divided by 0.0821. Are you working along at home, kids? Good. Divided by 293. That comes out to be 0.71. 0.71. Okay, 0.71. 0.71. Now, what are my units going to be here? This is the density, mass over volume. Okay. Now, in chemistry, we like to have everything in the proper units when it comes to mass. We use grams, and volume. That's actually liters. This will come out whenever you use the ideal gas law. Liters is what you need. You need to have liters. Okay. If you don't have liters, go to your grocery store, go to the soda pop aisle. You'll find some liters. divide by liters. So you will get grams per liter. This mass was at 18 grams per mole. So the gram sticks around for my mass unit, so it'd be grams per liter. And if you look at that, 0.71 grams in a liter. A liter is about, oh, yay big. 0.71 grams, not a lot. Well, gases aren't that dense. Okay, gases are just not very dense. So in a liter, I'm not going to have very much of it. Makes sense. Okay, solve that problem. I like that problem. It's a good problem. Hint, hint, hint. Okay, we'll stop this video for now. Talk to you soon.